Well, hello, Spain Park Chemistry. Here's another exciting edition of our online chemistry. This is part 4 of solutions. Okay, and so let's just go ahead and pop us open a new one here. Get you fired up. Woo! Let's do the do. Let's go ahead and do it. So in the last video, we ended up talking about these solubility curves. And this is giving us a concentration in terms of grams of solute per 100 grams of water. And that's how, in terms of solubility, sometimes to get a saturated solution, we talk about how many grams per 100 grams. And again, remember, if it has a positive slope, that means that as the temperature is increasing, solubility is increasing, it has a positive heat of solution, which means that these two values are greater than this one. We end up having a positive heat solution. So it takes more energy to break the bonds than the energy that's released when the water attaches via that ion to dipole or dipole-dipole attractions. Okay? Gases all have a negative heat of solution. And so their solubility always decreases with an increase in temperature. They're going to have a negative heat of solution. But that's all in terms of grams per 100 grams. Okay? What we want to talk about in this part is how do we quantitatively, numerically measure concentration of solutions. And there are 3 real ways to measure concentration. It's the amount of solute in the solvent, okay? And so it's just going to be a ratio. But the 3 common ways is going to be percent by mass, molarity, and molality. Now, if this were a normal school year, we would go through all 3 of these and learn how to calculate that. But we're having to kind of scale down here. And so the most important one of these is molarity. And when we measure molarity, okay, it's going to be moles of solute over liters of solution. You may have heard of ppms, parts per million. Well, this is parts per 100, and you just take the grams of solute over the total mass of the solution. And the only difference between molarity and molality is instead of doing liters of solution, you do kilograms of solvent. But, and this is kind of how you would make each of those solutions. So you can kind of look, but we're really just going to focus in, because of time, on molarity. And so molarity, now, you might think this is a typo, but the capital R, that is just so we can distinguish between molarity and molality. Molality has an L, molarity has the R, so we're just trying to distinguish between those two. And it's always going to be moles of solute per liter of solution. We use a capital M for molarity. All right? So you always understood it's 1 liter of solution on the bottom, but that gives you, now again notice, you have a conversion, you have a moles per liter. That's a conversion factor there between moles and liters. And yes, you can see what's coming, stoichiometry. Okay, so if we make a 5.5 molar solution, that means the molarity of the solution, there's 5.5 moles of NaCl for every 1 liter of the total solution. We then add in 1 liter of water. We added in enough water to make 1 liter, okay? So this is again the stress point. This is a measure of concentration, but notice that mathematically, this is the quality between 2 different units, moles and liters. So it's a conversion factor between moles and liters, okay? That is huge. That's why it's so important. It is the most common way to measure concentration, okay? So you really are going to have just 3 or 4 variables. Now, I'm just going to give you, if we look at molarity, is equal to moles of solute divided by liters of solution. And that's my abbreviation for solution. But the way we get moles is by taking grams over molar mass. So molarity is grams over molar mass, that's an M, divided by liters. So really, we have 1, 2, 3, 4 different variables. You're always going to be given 3. You're just going to have 4 variables. Given 3, you have to find the 4th one. So you should be able to do, if we just want to calculate the molarity here. So if I look at what is the molarity of a KCl solution, if 75 grams of KCl are dissolved in enough water to make 4.75 liters of the solution. Well, I'm given grams. So you can do this in 2 steps to where you can calculate the moles by taking grams over molar mass, get that value, and then plug it in here and go moles per liter. Or if you're comfortable enough with the math, you can just kind of do it all in one. You put your grams, you put your molar mass, you put your liters, 4.75, and then you just this divided by this on your calculator gives you the moles. Okay? So I expect that many of you all can just kind of plug it in and do it in this form, but if you need to, you can do it in 2 steps and find the moles in there. And that's kind of be how you're going to kind of see it worked out here. 75 grams, okay? So this is the conversion factor to convert it to grams to moles, okay? And so then we're getting moles and over the 4.75 liters, and we're going to end up getting it this way. So this is actually a third way to do it, okay? So you take the 75 grams divided by 4.75, okay? This is really just the conversion of converting the grams to moles. So how many moles of NaCl are in a 5 liters of a 0.67? This time, you know the molarity is 0.667, okay? You know it's 5 liters, so now you just plug it in here and here, and so you're solving for this one. So you know that to get rid of this, you have to multiply both sides to liters, okay? And so, well, I didn't finish that last one out. So here's 5 liters, okay? Times, notice you're multiplying both sides, times the molarity, 0.667 moles per liter. Notice again, that's the conversion factor between moles and liters. Now this is something super, super important. Molarity times volume equals moles. Every time, molarity, moles per liter, times liters equals moles. You need to I'm just going to take a second and let you let that settle in. There's just nothing better. All right, so now, what mass of KCl is needed to make 863 milliliters of a 1.33 molar? So I know I have 1.33 molar, okay? Now, this has to be liters, but hopefully you know that 863 milliliters, you move the decimal 3 places, it's 0.863 liters, okay? And so, you have to get your molar mass, but you already got that up here on this one. Here's your molar mass of the KCl. So you would just plug in here. Now, we're going to show you one way here, but the way I would do this is you can just kind of plug in. So we would know that molarity times liters is equal to grams over molar mass if we multiply both sides by liters here. Now I have to get rid of my molar mass. So then I can multiply both sides by molar mass. So now grams is going to equal liters times molarity, which is moles per liter, times grams over moles. And notice, liters cancel, moles cancel, and you end up with grams. And so this right here, this is really coming from this equation right here, just doing the math, and that's what you're going to see is how this is solved. Okay, so when we come down here, okay, so that's the conversion. Now, I recommend you just do that in your head and just move the decimal, but you can show it out, okay? Times the molarity, okay? So that's telling me how many moles I have, and then times the molar mass, which is my grams per mole, and that's going to give me my 84.9. So this right here is nothing more than rearranging this equation that we had solving for grams. So it's just algebra. Now, this is using units and dimensional analysis. Whatever's on top here has to go on the bottom there and help guide you and direct you. But it's all really just working around this one problem, this one equation, I should say. Again, 4 variables. You're going to be given 3 of them. You need to find the 4th. Now, sometimes it may be giving you moles, so you only have 3 variables, and you'll be given 2. Okay? So you have that, and the fact that it's moles per liter. It's a conversion factor, which we're going to look at next. Okay, so here's your comprehension check. So if you are in if you are not in advanced level chemistry, you can do this comprehension check, and that's the end. You do not need to go on to the next part of this video, which is we're going to classify as part 5. Okay, so you can pause the video, go ahead and do your comprehension check. Okay, if you are in advanced level, after you do your comprehension check, okay, go ahead, and then we're going to do just one last little step. Okay? So advanced level, this is part 5. Last part. Your favorite, stoichiometry. Okay? So I have a chemical equation. Most of our reactions take place in solutions. When I did this chemical reaction, I had 0.1 molar silver nitrate. And I made a solution of potassium chromate. So many reactions take place in solutions. So we need to know how to, the molarity tells us how many moles there are in a given liter. So it gives us a conversion factor to moles, which is what we need. Everything we need in stoichiometry is convert to moles. So what mass of precipitate is formed, okay, is 755 milliliters of 0.855. Okay? So I'm hoping that the glare is not too bad on here, but I like to, when I see something like this, I want to say, okay, I have 755 milliliters of a 0.855, Steve, 855, I've forgotten how to write as well, 0.855 molar, okay? Now, but you have to realize that that really means moles per liter, okay? Molarity is moles per liter, so I'm even going to go ahead and just write that as moles per liter, which means that I'm going to have to make this liters, okay? But I know I can do that in my head, 0.755 liters. But here's what's the question. What mass of the precipitate? Well, the precipitate is the solid. That's going to be this one, okay? So I'm looking for X grams of this. So I know it's a stoichiometry problem. Number 1, I'm given a balanced equation. Number 2, I'm given information about one thing, one substance, and asked to find something else out about the other one. So, in every stoichiometry problem, you have to take the given and convert it to moles. Okay? You have to take the given and convert it to moles. Well, the given is this. This is my conversion factor. Okay? Start with the thing that only has 1 unit. The thing with 2 units is the conversion factor. So instead of going grams to moles using the molar mass, we're going to go liters to moles using the molarity. So it's actually easier again because we don't have to calculate the molar mass. All right? So when we go through and we look at that then, okay, here's your 0.755 liters, it's just already been converted, okay, times the molarity, because if I stop right there, that tells me how many moles of silver nitrate, because liters has canceled right there. Now, to always go from moles to moles, I have to use my my coefficients. Now, there's understood ones written right there. So I'm going to have 1 mole of silver chloride for every 1 mole of silver nitrate. So now, if I stop right there, I'm left with moles of silver chloride. But the question wants what mass, which we know to be grams, so we know our conversion factor between moles and grams is our molar mass. So you go and you calculate 107.9 plus 35.45, you end up getting your molar mass of 143.323, carried out even a little bit farther than what I just said. But now notice that moles of AgCl cancel, leaving you with grams of AgCl, which is what we want. So this is identical again to all the other types of stoichiometry problems. You take the given to moles, okay? So if it's grams, you use the molar mass. If it's a gas at STP, you use 22.4. If it's a gas not at STP, you use the ideal gas law. Now if it's a solution, you use the molarity to convert to moles. But it's always given to moles use the mole ratio, balance from the coefficients from the balanced equation, and then to go back to grams. Okay? So it's a very simple, straightforward problem, just like all your other stoichiometry problems. We're just adding in a new conversion factor, but it's given in the problem. Okay? So, maybe take a second, pause this video, see what you can do with this one. Okay? What mass of silver metal will be formed by reacting 433 milliliters of 1.22 molar AgCl solution with excess of zinc nitrate? Pause the video, see if you can do this. All right. So, again, here's my given. But I know that this is molarity, so I know that it's moles per liter, so I know this needs to be liters, so I know it's going to be 0.433 liters. Okay? 0.433 liters. Now, I'm going to have to convert that. The first step is to take my 0.433 liters of what mass of silver metal will be formed by reacting milliliters of silver chloride, okay, with zinc. Okay? So, this is the concentration of my silver chloride. Now, I have to use then the molar mass of the silver chloride. And that molar mass. I use the given molarity of the silver chloride. Okay? So that gives me moles of silver chloride. Now I have to use my ratio. My unknown and my known. Again, it's a 2-to-2 ratio. And now I need to go to grams, so I'm just going to use the molar mass. Okay? So it's the exact same process as all of your other stoichiometry problems. We're just going to use the molarity as the conversion factor. Okay? All right. Well, this one just has it all worked out right there for you. But here's another example. I don't know. It just automatically is popping up. So, H3PO4 plus 3 NaOH. Here's my balanced equation. How much 0.2 molar is needed to react with 100 milliliters of 0.1 molar? So this time it's molarity and molarity. So again, I change my 100 milliliters to liters, 0.1. Multiply that by the molarity, which gets me moles. Okay, liters are now canceling. Then I use the mole ratio, 1 mole of H3PO4 phosphoric acid for every 3 moles of NaOH. So it's always what you're looking for, what's given. Moles of NaOH needs to go on the bottom. And then I'm going to use the molarity, but since moles is on top, I'm going to put the 0.2 moles over 1 liter. I'm going to put the 1 liter on top here because I need moles to cancel out. So it's going to take 0.0166 liters, but you round that to 0.017 or 17 milliliters. So you would have to take 17 milliliters of this 0.2 molar phosphoric acid to completely neutralize 0.1 molar NaOH. Okay, that's what we just found. But again, the molarity is the conversion factor between liters and moles, moles to liters. You can use it at the beginning, you can use it at the end, you could use it both. This is a molarity to molarity problem. Okay? So, here's a comprehension check, a couple of them for you to try to do on your own. Okay, and again, if you have any questions, email your teacher and let us know. We'll be glad to help you. We will be putting out the answers to these comprehension checks, as well as I'll do a quick review video of all the comprehension checks for solutions at the beginning of the next week. All right? But again, try to keep up, show your work, do these on a separate sheet of paper, and just kind of keep it for your notes to study for. And we'll get you a study guide, and then after we go through and do some practice worksheets and a study guide, then we'll have a test on this. But that concludes all of the notes for solutions. Okay? Hope this is helpful. Hope you're learning something. And again, feel free to subscribe to my page.